Hello and welcome to Coffee and Control, the podcast in which I find fascinating people working within the field of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and my guest today is a researcher who has very recently moved to the University of Southampton. So if you listened to last month's episode, we talked a lot about behavioural systems from a theoretical point of view. In this episode, we focus more on the application side of things and give some examples of systems where this approach is really useful. So I was very much a fan of this guest before going into his interview, just from reading his papers. And then I actually started talking to him, and honestly, he's so lovely. Like, I genuinely had a neck ache at the end of the interview from just nodding at him too enthusiastically. So get ready to find out about the applications of behavioural systems theory, switch systems, a ton of different approaches to the control of power converters, data-driven control of power systems, and advice on dealing with the darker side of academia with my guest this month, Dr. Jonathan Mayo Maldonado. Could you start by saying your first and last name and a few sentences introducing yourself and your research?
My name is Jonathan. I'm from Mexico. My full name in Spanish would be something like Jonathan Mayo Maldonado, but it's a very long name, so in English it's okay, Jonathan Mayo. I have a background in electronics and electrical engineering in general, from bachelor's, master's, and PhD, and my main specialization is power electronics and control.
Okay, so most guests, the first question I ask them are about their PhD work, but I noticed you'd written a lot of papers on kind of experimental implementation of various controllers even before you began your PhD. So I was wondering, how did this come about and what drew you to research in the field of control?
Well, I think it starts for undergrads, usually having inspiration from certain teachers that are very good at something, and then we get motivated. I had very good teachers in control, actually. That's why I was interested. And then I started to work on projects with them. I mean, completely independently from my coursework or anything. I just, with my own initiative, I wanted to do something else, like an extracurricular activity. And in that case, it was about control. And I learned a lot, and I did a lot of experiments in control. I mean, basic control techniques, but it was very good or enough to give me some motivation about continuing. So I started those, and we had the pleasure to publish a few papers in conferences and a few journal papers, as you said before, starting my PhD.
So your PhD was titled Switched Linear Differential Systems, which you did at Southampton, supervised by Paolo Rappisada, who I interviewed in the last episode. What led you to doing your PhD in this area? So kind of why control and why switch systems?
To be honest, I was very ignorant about control theory. So even when I was working with control systems or control design, my idea was actually very basic. When I was a master's student, I thought, I know now how to implement controllers, I mean traditional controllers with traditional theory. And what I would like to know is how to design my own control laws or my own control techniques. And I found out that I didn't have the mathematics to do that. So my idea, in a very naive way, I could say, was let's go for a PhD that is very mathematical oriented. Then since I know now the experimental part, I need the theory. And that was very naive because I didn't know that it was so difficult, actually. So my thesis was very theoretical. And in the case of switch systems, I had in mind something as power converters because they have switches. So my idea was, if I know the mathematics behind the control design for switch systems, maybe I can apply it for power converters. And that made sense to me. That's why I went for it, but it was very difficult because it involved a lot of theory, and I didn't have the background actually for mathematics. So I underestimated the effort that it took. But eventually I made my way, I mean, with a lot of effort. I don't think that I wrote a thesis at the level of a mathematician, but I think we did some reasonable mathematics anyway, but it took a lot of effort.
The effort Jonathan put into his PhD clearly paid off, because his thesis is an absolute joy to read and also led to him being awarded the Doctoral Control and Automation Dissertation Prize, which, in my opinion, very well deserved.
Now, looking back, perhaps I would advise me to go for a less theoretical PhD, but we are here, and that is a lesson to learn.
I was going to edit this in an aside, but I wanted to say the thing that I loved when reading your thesis was that you'd give some maths and then you'd be like, here's an example where you can actually use the maths and like see how that actually applies to real systems.
Yeah. That is actually that was very much necessary for me. That is the way in which I learned mathematics. So I had to see what was the connection with the real application in order to understand the mathematics, because I think in all my days as an engineering student, I shaped my brain and my mind in terms of physical things. So I didn't have the abstract of the mathematics.
I think this might be the exact point in the episode where I low-key fell in love with Jonathan, because I relate so hard to having had my brain shaped by an engineering degree in a way that sometimes makes it really hard to work with abstract mathematics and be as precise as you often need to be when writing a paper or doing research in control. But Jonathan is living proof that it is possible to reshape your thinking and somehow come to a nice middle point where kind of theory and application connect and it all makes sense.
So that's why these examples were for me, actually. And then my supervisor said, oh, those are very good. I mean, because for him, it worked in the opposite way. He knew the abstract, but he didn't know about the application. So it was nice in both ways. So he said, you should put this in your thesis. Every time you have one mathematical example, let's do the application or the physical interpretation of it. So I enjoyed that, actually. It's a kind of signature in my thesis, yes.
So, your thesis focused on developing new mathematical tools for analysing switch systems, specifically looking at this from a behavioural perspective instead of the classical approach of switching between different state space models.
Mm-hmm.
So, could you explain what the issue or challenges are with modelling switch systems using the state space approach and what the benefit of using the behavioural approach is?
Yes, I think this is, in general, state space representations are quite rooted in systems and control. So when we talk about the system, either linear or nonlinear, basically we are thinking about a state space system. So writing down equations in terms of first order differential equations, the model of systems. I mean, this has several reasons. I mean, historical reasons, and also so in terms of practicality, it's very useful to have a state. But from the behavioral point of view, we are not very much interested in representations, in state space models. We are interested in trajectories. And the set of trajectories that satisfy the physical laws of the system are the behavior, basically, of the system. So we have a mathematical object that is a set instead of a representation. And that set of solutions can represent many different representations. I mean, transfer functions, state space, or higher order differential equations. And among that, I think the most general way of representing a system, at least in linear terms, is with higher order differential equations or linear differential systems, how we call them. So you asked about what is the limitation, or did you phrase it in that way? The limitation of state from the state space approach for switch systems? Well, basically, because when we have a representation, we are thinking about global state space, that all the systems that are being switched share the same state space. And that is not justified from physical principles or from physical observations, because just the point of connecting or disconnecting things, which is a switching phenomenon, increases or decreases the complexity of the system. So what we have in reality is a system whose state space is changing all the time. If we use state space representations, the only thing that we can switch is the parameters of the system, but not the order of the system. So from the behavioral point of view, we can change the order of the system as well, because what is most general, as I mentioned, is the behavior of the system, is what the phenomenon that we are observing. So we can concatenate, for example, solutions of differential equations with different order in the behavioral approach. And this was justified also from physical or practical experiments of power converters whose state space changes during the switching.
Now that we've covered why the systems you studied are kind of important, could you explain what a switched linear differential system actually is and the different components that make it up?
Well, that is a very good question. Yeah, it took a lot of time actually to work out the components of the switched linear differential system. So we saw it in terms of trajectories. Okay, I have a system that generates a trajectory that can be a voltage, a current, a velocity in a physical system. And now something happens, the dynamical laws of the system change, including its state space, and then we continue. And what is the solution of the next system? So the components are then the systems, the bank of systems that are being switched. And the other component is, of course, the switching signal, which is the pattern at which these systems are changed. And the third component would be something that we call the gluing condition. So it's an algebraic condition that determines the initial conditions at the moment of the switching. And what was very nice to see there is that these gluing conditions have a physical interpretation in terms of power or energy conservation principles, or in general conserved quantities. For example, how to model the gluing condition would be something like using the law of conservation of charge or magnetic flux, in general conservation of momentum in mechanical systems. So they are part of the modeling. So these are the kind of things that we need to model a switch system. As I said, the modes, the dynamical modes that are being switched, the switching signal, which is the pattern at which they are switched, and the gluing conditions, which is what basically glues the trajectories when we are switching, and they are enforced by physical principles.
Because I was really intrigued by the gluing conditions. So partly that they are actual kind of physically motivated, but then also the fact that when you have two switch systems with the same dynamics but different gluing conditions, then you can get different stability properties, is something that you mentioned. Could you elaborate a bit more on this? And was that surprising when you discovered that?
Yes, it's surprising because when we study stability of switch systems, we have some issues. For example, we can have stable modes. So we switch among stable modes, but the switching can bring instability. So if we switch so fast, at some point the trajectories can blow up, basically. And this has to do precisely with some underlying properties of the systems. For example, if you keep increasing the trajectory every time you switch, then you will get instability or unbounded trajectories. But also from the point of view of the gluing conditions, which are basically like resets. So every time you switch, you assign a new set of initial conditions. Then imagine that you switch so fast and your reset is increasing the values of the variables. So in this case, you can get an unbounded response as well. What is very beautiful from the point of view of physics is that the gluing conditions from physical principles always bring a sort of stable pattern, so precisely enforced by conservation principles. So, for example, you cannot simply increase energy out of nothing. When you switch, it doesn't matter how fast you switch, you always tend to conserve the same energy at the switching or lose energy. So that is how the gluing conditions are involved in stability. So for general systems, what we want to do is to, in a sense, mimic the behavior of the nature that brings always the stable pattern.
Because the next thing I was going to ask you about was about stability, because at least one, maybe a few chapters of your thesis were analysing the stability of switch systems. So I went back and fact-checked myself, and stability was mostly covered in chapter 5 of Jonathan's thesis. The entire title of that chapter was Stability of Switched Linear Differential Systems. But it was also touched on a little bit in chapter 6, mostly regarding the relationship between stability and dissipativity, which we're going to talk a little bit about later on in this episode. Could you explain how the approach you used was able to ensure that the switch systems that you designed were stable?
Oh, yes. I mean, in control theory, we have usually something very powerful, which is Lyapunov theory. So if we have a Lyapunov function, this is basically equivalent to stability. In the case of switch systems, we have something like multiple Lyapunov functions. So then the only thing that we need to do is, just as in the traditional case, a Lyapunov function, we must prove that its derivative decays with time. Well, this is true for switch systems. I mean, every time we switch, there is an associated Lyapunov function that decays with time. But another condition is that when you switch, the Lyapunov function doesn't increase. So it can decrease abruptly, or it can be smooth, but keep decreasing as we switch among the modes. And then this is basically the concept of multiple Lyapunov function.
So your initial work was just looking at autonomous systems, so without any input, and then you extended this to non-autonomous systems. So what are the differences between controller design and analysis in these two cases?
Yeah, well, this is a very good question. Well, autonomous systems are those whose future depends completely on their past, that there's no external component affecting them. Those systems could be even closed-loop systems with no set points. I mean, if we want to stabilize, for example, at the origin, then we can do that with a controller, feedback, for example, and that is an autonomous system as well. There are limitations, of course, because if we want, for example, to do trajectory tracking, if we want to do regulation or disturbance rejection, some other scenarios that we find in engineering very much, then we need to consider open systems. And open systems also have certain properties in terms of stability, for example, input to output stability. And then we found it necessary to involve this from the point of view of switch systems. Now, what are open switch systems and what type of stability properties can we exploit from there? And we did it using dissipativity theory, whose special case is very well known, passivity. So we were interested in analyzing those properties, but let's say that is about extending the cases for the type of applications.
Now, you might remember from last month's episode with Paula Rapisada that a dissipative system is one for which there is more energy going into the system than coming out. And something we didn't get around to discussing was a relationship between dissipativity and stability. But I wanted to mention this a little bit here. So Paula wrote a paper back in 2010 titled Stabilization, Lyapunov Functions and Dissipation. And in the introduction, it stated, in the linear setting, stabilizing a plant amounts to imposing dissipation on it. Passivation with respect to a suitable supply rate is necessary in order to achieve closed-loop stability. And section 3 of this paper, where they introduced the theorem and proof that actually shows this, is very simply titled Stabilization is Dissipation. In terms of practical applications of the work you developed in your thesis, so Chapter 7 focused on applying this framework to energy distribution networks. So what is the disadvantage of the classical state space averaging framework when dealing with these kind of systems?
Well, I think, I have nothing against the state space. Actually, I do state space as well. But the way I see it is that I do what is simpler. Usually in engineering for control design, we think in something that is very practical, where we need the least amount of sensors or the least computational resources to solve this in real time, things like that. So I usually look for those. Then I use the approach that makes those things simpler. From the point of view of higher order differential systems, for example, behavioral approach, something that I liked is the idea of working on external variables. With external variables, we mean the input and the output. And in that case, the output is the to be controlled variable, or the variables that we have access to, the variables that we can measure. So I would say that one disadvantage when we work with state space is that we have so many states, usually, depending on the order of the system, and then we need a lot of sensors to measure those variables and act upon those variables, right? From the point of view of behavioral system theory, if we focus on external variables, we can prove the same things: stability, we can do control design without thinking about having so many sensors or so many signals. So in that sense, it makes sense to me because, for example, you mentioned distribution networks or energy distribution networks. We have sometimes so many nodes, a very high order, but we don't have access to each of the nodes. We don't have so many sensors. So how to do control anyway? So that's why I think it's a benefit to do it in a higher order case or with behavioral system theory.
So my understanding is the key issue you were addressing in this work was that of negative impedance instability. What is negative impedance instability, and how is your switch linear differential systems framework effectively able to deal with this?
Okay, that is a very good question. Yes, the negative impedance is something that is an approximation of something that happens in the sense of nonlinear systems. So when you have something that is called constant power load, it's basically a load that maintains a constant power. And this doesn't exist in a passive way. It's a non-passive system, and it's also a nonlinear system. Usually in practice, this is a converter that is very good at controlling its voltage, and it's so good that it maintains a constant power at its terminals, input terminals. So if we feed this converter with another converter, then from the point of view of the source converter, this is a constant power load, and this brings an unstable equilibrium, basically. The way in which we express this is if we approximate by linearizing the constant power load, we get a negative impedance. And a negative impedance can be linked to an unstable equilibrium point. Now, from the point of view of switch linear differential systems, we analyzed this in terms of an open system, as we mentioned already. In the open system, we analyzed the way in which it changes energy with the load. And then with a controller, we were able to impose a dissipation constraint that makes the system input to output stable. So just to put it in very simple terms, it's a way in which we can shape the energy and the power of the system in such a way that it brings stability.
So I kind of like to move on now. I guess a related topic of DC-DC converters. Could you start by giving a brief outline of what a DC to DC converter is and kind of a brief overview of some of the different types that you've worked with?
Yes, well, DC converters are some already old technology, actually. They were known as switching power supplies. They were called like that because it's the counterpart of linear power supplies. Both are implemented using solid-state devices, transistors. The difference is how we operate them. For example, a transistor operating in its linear region would bring a linear power supply. If it is operating in the saturation and cutoff region as a switch, then it's a switching power supply. So the benefits of a switching power supply, in this case a DC converter, is that is the efficiency, because at any given time, ideally speaking, there is no dissipation of power in a switch because either the current or the voltage is equal to zero. So the product is always equal to zero. And then that's why they are very, very beneficial. Now, they were old technologies. For example, buck boost converters that were very well known. But when we had this boom of renewable energy, there was a lot of attraction in terms of developing new topologies to deal with some specific issues in renewables. For example, having very low voltages generated by solar panels or fuel cells or batteries, and then you want to increase this voltage in such a way that you can connect it to the grid, for example. Then you can do something useful with it. Then there were plenty of new topologies coming up, having high voltage gains that could do this. And then we started to see that the traditional control techniques that we had for the well-known converters, the boost, buck boost, the typical ones, didn't apply. So then there was this need then to design new controllers. And there are plenty of new applications. For example, we have interleaved converters where we cancel out some harmonics in the current, things like that, and they require more sophisticated control techniques. So that is answering the question what they are. Well, DC converters is basically a converter that transforms power in one form into another, in this case in terms of DC. And this is how they're being used now for renewables mostly.
So you've mentioned this a bit already, I think, but could you explain how DC-DC converters can be represented as a switch system and what the control objective is for these types of systems?
Yes, well, to be honest, it's not always the best way, because in switch systems, the problem that we have is when we have many switching states, then your bank of systems is very large. Mm-hmm. If you have, for example, thinking about a system with 4 switches, you have 2 to the power 4 possible states. Then as you increase the number of switches, you have a bank that is very large. So it's not always a good idea to use a switch systems approach. But just answering the question, in the case of converters like the boost converter, the buck boost, they have only 2 modes. So the way you represent it is by starting, for example, when the switch is in one position, you write down the differential equations of that circuit, and then you put the switch in the other position and write down the equations for that mode. Then you have 2 sets of differential equations, and then your gluing conditions that we mentioned before are the conservation principles that enforce the switching, the new initial condition after the switching. And you mentioned also, you asked about the control objective. Well, the control objective depends on the application, but in many cases is the output voltage. For example, find the switching signal in such way that you reach a certain voltage and you keep it there despite of disturbances or changes in the input. For example, if you have a solar panel that is changing its voltage when there is a cloud or something like that, then you want to compensate for that. Then the switching signal enforces that regulation.
So you've explored the use of a number of different controllers for DC-DC converters throughout your career. So I picked out a few papers you've written in the past kind of 5 years or so that I'd like to go into in more detail.
Yeah.
Okay. So the first topic I'd like to discuss. So you've mentioned already issues with constant power loads. So a lot of the work you've done is designing controllers to deal with issues arising from these. Why can constant power loads cause instability issues?
Okay, there are several ways to explain this. For example, from the point of view of electrical engineering, the constant power load causes instability because it enforces an unfeasible power flow. So there is a power flow that we intended to direct from the source to the load, and this power flow is unfeasible. It's not possible, physically speaking. From the point of view of control, the constant power load simply brings a system, an interconnected system, which has an unstable equilibrium. So any slight disturbance will make you diverge from the equilibrium and cause very weird oscillations and things like that. So in a sense, those 2 reasons are the same, simply expressed in different ways. One from the point of view of mathematics in terms of equilibrium, and the point of view of electrical engineering is just an unfeasible power flow.
One of your papers in this area was concerned with power shaping control for these types of systems. So my understanding is this involved designing a controller to shape the power dynamics in order to induce passivity. Could you elaborate more on this, and particularly why issues with passivity can cause a system to be unstable, and how your design controller was able to deal with this?
Okay. Yeah. I think that paper that you're mentioning in particular had this idea of using these 2 interpretations that I mentioned in terms of the unstable equilibria and the unfeasible power flow. What happens is that in general, a power converter in open loop, it's a passive system. So there's no way in which the converter can just generate energy spontaneously by itself, right? It's just passive, it absorbs energy. But when you connect it with the constant power load, since the constant power load is another converter, it can return energy to the source converter. So this is a system that is no longer passive. It also generates energy in the sense that the load is reverting the power flow. So the idea of power shaping was basically doing passivation. So with a controller, converting the system that is originally non-passive into a passive system, and this automatically brings this feasibility of the power flow. So that we ensure with the controller that the power flow always goes in the right direction from the source to the load. And that is a property of a passive system. So that's why we called it like that, power shaping, trying to make sense of this intuition about the feasibility of the power flow.
So another paper that you wrote involved designing nonlinear controllers for these types of systems using what you called lifted coordinates.
Yeah.
So could you explain a bit more about where this idea came from and how it helps with controller design?
Oh, yes. Well, during my thesis, during most of my work, even for this power shaping technique, we always used linear systems or the linear system setting. Because we like linear systems, because we have plenty of tools there. I mean, stability is easy to determine. I mean, it's very clear what we can do in linear systems for optimization and lots of things. But power converters in general are non-linear systems. So I always wanted to do some nonlinear control. I had a bit of background in nonlinear control. So the idea of this paper now was analyzing everything in terms of nonlinear systems. But yet, a bit of a contradiction in this is that we found a way to use linear techniques also to control nonlinear systems. And the key for this was precisely using lifted coordinates. What lifted coordinates are basically that instead of addressing the problem from the point of view of voltages and currents, which are state variables, we address it in terms of lifted coordinates that are power and energy. So there is a nonlinear map between power and energy and voltage and current. And this linear map is, for example, let's say that you have a current through an inductor, let's call it I, then your energy stored by the inductor is 1/2 of L times I squared. So that is a nonlinear map. So it maps the I into something nonlinear, but it turns out that when you lift this with this map, now the resulting system is linear. So the power conservation equation that you get is an almost trivial first order differential system that is linear. So then what we did is using applying control techniques for power and energy. And then since we have the map to go back to linear coordinates, and we just did it and implemented the controller. So it was a nice trick using a change of coordinates just to linearize.
Two of the controllers that you explored in this paper involve steering the output voltage to a desired value by getting the current to track a particular trajectory, rather than manipulating the output voltage directly. But I understand this was kind of the standard approach used when you were writing this paper, or kind of what everyone else was doing. So why was this something that everyone was doing at the time? Why was it thought to be necessary?
Yeah, well, this is an issue that has been there always in power converters. In most of them, they are non-minimum phase systems. So this means that if you linearize and get a transfer function, they have an unstable zero at the numerator of the transfer function. And this brings some sort of awkward situations. In the frequency domain, we see that the phase doesn't get constant. As you increase the frequency, it decreases a lot. So that's why it's called non-minimum phase. This limits the bandwidth of the converter, which in terms of in the time domain, this means that you limit the speed of the response of the converter. So if you want a converter to be very quick at compensating, if you control the voltage directly, since it is a non-minimum phase variable, then you cannot do it without reaching stability very quickly. Then this doesn't happen when you swap the output variable to current, which is kind of a bad thing in terms of practicality, because usually we want to control the voltage, not the current. But if you control the current, then this is a non-minimum phase variable. You can have the full bandwidth. I mean, you can have very fast compensating controllers. So what we do usually is using indirect voltage control, that we control the voltage through the current. So, and this is very common in the community.
If you would like to learn more about control design for non-minimum phase systems, you might be interested in listening to the very first episode of this podcast, if you haven't already, in which I interviewed Professor Chris Freeman, my wonderful PhD supervisor, whose own PhD was devoted to designing iterative learning controllers for non-minimum phase plants. So I think you mentioned it's not really ideal to control the voltage via the current. So there was a paper that you published a few years later that proposed an approach that was actually able to implement direct voltage control, so titled Direct Output Voltage Control of Non-Minimum Phase Higher Order DC-DC Converters. Could you give an overview of this paper, kind of how it came about and how it solved the problem of non-minimum phaseness?
Oh, yeah. I mean, this is very interesting, actually, because this came out of an observation. I remember I asked a student, I had a PhD student, a very good PhD student. I asked him to check if he could implement a controller with direct output voltage feedback. And I was trying to make a point to him that it will reach instability very quickly. But it turned out that he came with the results and he said, no, it works. Then I said, it cannot be. Then we started to have a look at the problem over and over again, and then we found that there is a case in what we call higher order converters. I mean, I mentioned, for example, boost, buck boost converters. There are second order systems, but we have other types of converters like choke, CEPIC, or many other topologies that are being developed in power electronics that have that are fourth order or fifth order. I mean, you have plenty of components now. It turns out that you can do direct output voltage control with those under certain conditions and also with certain limitations. But we can truly match the behavior of current control and voltage control, direct voltage control, in higher order converters, so which was very good. It's something that I didn't expect to happen. We formalized the theory eventually out of this observation of my student, and then we implemented it.
The PhD student in question was Enrique Garcia Arias, and his PhD was titled Development of Control and Communication Tools for DC Microgrids, which I have linked in the description.
The reason why this is good is because if you do current control, you usually need an additional sensor, a current sensor. If you do direct output voltage control, you only need the voltage sensor, one instead of two, which is very good. I mean, you can save, if you think about mass production of devices, I mean, a power converter is an electronics device that is produced massively with thousands of devices. So if you just reduce one sensor in those thousands, then you save a lot of money. So that was the idea, and I like that very much, that result.
I would like to move on now to your work on data-driven control. So I guess kind of makes sense to start with the work on DC microgrid configurations, as we've just been talking about DC-DC converters. So what are the difficulties faced when using a model-based approach to control of these networks?
Okay, yeah, this is a very good question. Actually, this is a debate that we have usually with colleagues in control, because a lot of people are completely model-based and then are not convinced, for example, from data-driven approaches. But again, what I do usually is that I'm not driven by the theory, but by the applications, and I want to do what makes sense from the application point of view. From the application point of view, we have, for example, you mentioned a microgrid where you have plenty of devices connected. So you have a very high order system. Then you can do two things, either working with a system with very high order and deriving controllers with something with a state space which is ridiculously high order, or you can make assumptions. And then you make assumptions that what you have at the input of the converter is constant and what you have at the output is also constant. But we already mentioned a case which is very simple when you have another power converter connected at the output as load that behaves as a constant power load, then you have instability. So the assumption doesn't work even in the simplest possible case. Now think about the case when you have plenty of converters, you have a network of converters, then you need to be very careful about the assumptions or deal with a lot of weird phenomenon due to the instability or oscillations due to the highly complex dynamics. So from that point of view, the idea that I had with data-driven control, or why I embraced the idea of data-driven control, was what if we don't have access to all those systems that are interconnected? And we want to control one converter, but we don't know what are the dynamics of all the things that are connected around it. But we can infer those dynamics from data. And if we could guarantee stability in the same way as in a model-based, then it is quite an advantage that you don't need to actually know what is connected to the network. I mean, you just measure data and get your controllers and guarantee stability coming from that data. And it has been very good, very successful in the sense of applications, because you don't need to think about having models for everything, which is the point of data-driven control.
So could you explain how the data-driven control you use actually works? Like, how do you go from here's a bunch of data to actually being able to control a system based on that?
Yes, there is, I like this phrase that is in some papers. I always write it in this way. The process is replacing models with data. This means that we want to get from the data the same information that we get from the model. And if we think about it, that is what a model does. It provides information. It's simply that the information from the data and from the model come in different ways. One is completely numerical, and another one is in terms of a representation of the differential equations. So the process works from the point of view of system identification, which is well known in control theory. So from data, you can derive a model. So what we did is trying to shortcut this, because that would be a process like identifying the model and then going to the whiteboard and write down the equations, and then let's design a controller with this model. What we wanted to do is to do it completely numerically, automatically. So the way in which we do it, roughly speaking, is that we construct a matrix of data. Then from that matrix, we derive something through factorizations that is a coefficient matrix that reveals what are the parameters of the system. So it's a way to condense the data into a parameterization of the system. And then with that parameterization, we devised a Lyapunov condition in terms of linear matrix inequalities, and then we can derive controllers numerically from there. So from the matrix of data, we get this coefficient matrix with the parameters. With that coefficient matrix, we plug it in a linear matrix inequality and derive basically the gains of a controller.
So you mentioned in one of your papers that proving stability for systems with active loads was very challenging. We've kind of touched on stability already. So I was wondering how the data-driven control approach that you used was able to kind of succeed in proving stability of these systems where other approaches had failed.
Well, I would say that it's not necessarily that other approaches fail, but as I said before, I'm interested in the practicality of things. So what is practical? What kind of approach can give me the less number of assumptions or can be easily implemented with what we have? So, for example, I mentioned that typically what we do in, for example, imagine a factory of power converters. They don't know exactly what you are going to connect to the converter, the load, but they make some assumptions on it. For example, the level of power that you are going to extract from the converter, and then they can work out the value of the resistance or an equivalent resistance, and then they design a controller with that resistance. When we, instead of connecting the resistance, we connect something else, like an active load, then we can have, for the same specification of power, we can have an unstable mode, simply because the load has dynamics, which was an assumption that was left out of the control design. So from the point of view of data-driven control, the idea is very compelling because of using data, because it doesn't matter what you connect to there. From data, you can infer the dynamics, and then you can guarantee stability using such information. So that's why I think it's very useful. I am pretty sure that there are model-based approaches where you can do something similar, for example, with adaptive control that you estimate using a model. But the point that we have is, why bother? I mean, why bother having a model or being so obsessed with models if you can avoid it and implement it in a practical way as well. I mean, that's why we liked it. From the practical point of view, I think it's justified.
Okay, so a kind of slightly different but related application of data-driven control you've explored is enhancing the performance of power grids. So kind of, is it AC instead of DC? What are the differences regarding control for AC versus DC networks? Can you just apply the same techniques in the same way, or do you have to change your approach?
I think you have to change your approach because when you work with AC systems now, when you want to stabilize something, now you are talking about stabilizing an AC trajectory instead of a constant value, right? So in that sense, then you need to change your approach. If you work directly in terms of AC systems, you take the sinusoidal signals at face value, and then you track a trajectory using something like repetitive control or proportional resonant control. I mean, which is the generalization of a PI in DC, but for AC trajectories, for example. Or another way that is very popular is transforming the AC trajectories into DC trajectories using a change of coordinates. And this is called DQ transformation. So you transform from a general frame that is rotating into a frame that is stationary using time variant transformations, which are depending on the frequency of the system. So that's why it's not that simple just to translate from DC to AC. And also there's another thing in terms of power. In DC systems, we have only active power, but in the frequency domain, in AC systems, we have active and reactive power.
I feel like active and reactive power is something that is very basic electrical engineering knowledge, but it's also something I had completely forgotten about until I had to teach it to my foundation year engineering students a few weeks ago. So, for anyone who might be unaware or could benefit from a recap, when you have an AC circuit, you generally get current and voltage waveforms that are out of phase with each other. And this basically means that there's some component of the waveform that results in net transfer of energy, which is the active power. And then there's another component where there isn't any net energy transfer, which is the reactive power. The details are not entirely easy to explain without using a diagram, but I've left a link to a video where they explain it a lot better.
And both have certain physical interpretation and also consequences. So in AC systems, you have to control also reactive power, which increases the level of difficulty, which is what we do when we control inverters, for example. When we interconnect renewable energy into the grid, we need to do it in AC, and that's the type of controllers that we need.
So again, there's kind of a few, I think two or three papers that I'd like to discuss in a little bit more detail. So in 2020, you published a paper examining how the data-driven frameworks you developed could be used to detect topology changes in distribution networks. So specifically, you were looking at using data from distribution level phasor measurement units. So I guess my first question is, what are DPMUs and what are the difficulties associated with using measurements from these?
Well, distribution phasor measurement units are also called micro PMUs, micro phasor measurement units. They are basically a refined version of phasor measurement units. They were, I think, developed in the 70s to get data from the transmission network. The transmission network is the high voltage part of the network, and they have very long transmission lines. And associated to them, there is an inductance that has certain value. I mean, as you increase the distance of the line, you increase the inductance. And when you increase the inductance, this means that the voltage in one point and another, I mean, the two ends of the transmission line, has a phase that is significantly different. Okay. Now, this was very good because you didn't need a very accurate phasor measurement unit to measure this difference in phase. Then you can have data because the phase gives you information about the phasor, which is the magnitude and phase angle of the voltage and current, which gives you very much what is the status of the network, for example, for monitoring purposes. In distribution networks, this idea is much more complicated because the distribution lines are very short. then the difference of the phase angle in two ends of that distribution line is very small. So you need a very accurate device. And this is what happened with the micro PMUs. They designed these devices that are very accurate in such a way that they can measure in a micro level this phase difference. I was very much interested in this topic because I was involved in a project with some colleagues from the University of Berkeley in California, and they were working with this technology. And I was very excited because now it was like having real data in real time coming from the network. And then we started to analyze and we said, okay, what we can do with the data. And let's say that the lowest hanging fruit in terms of applications is doing system identification or fault detection. So then we used this technique that I mentioned before. From the data, we obtained a coefficient matrix that parameterizes the network, and then we monitor the changes in those parameters. And then we could associate those changes with a particular fault in the network, for example, a short circuit or an open circuit. You asked also about the difficulties. There are plenty of challenges there. I think there is a lot to do, for example, in terms of cybersecurity, which is a topic I'm very interested in now. For example, what happens if you are hacked and your communication channels where you receive the information from PMUs are hijacked and you get false information. You can, for example, have information that there is certain fault when there isn't, and then you deploy a protection mechanism that instead of helping, it is causing some detrimental effect on the network. So I think that is one of the difficulties now to protect such data.
So the final kind of technical thing I'd like to discuss is a paper you published last year titled Data-Driven Optimal Voltage Control Index Tracking in Active Distribution Networks, which kind of seemed to draw together a lot of your previous work in this area. So the first question I'd like to ask is relating to the rise in renewable energy in electric vehicles. So what impact does this have on distribution networks? And in relation to this paper, how does this link to coordinated distributed energy resources?
This is a very interesting topic, actually, because I think there is no question that we need more renewables. We have net zero objectives. We also want to change from diesel or petrol vehicles to electric vehicles only. There is also, for example, plans to ban the selling of new fossil fuel vehicles. I think there are lots of challenges on that, but the main idea is just shifting the paradigm to fully electric and to fully renewable or clean energy. So there is no question that that's a need there. The problem is the type of challenges that we bring into the network when we talk about integration of electric vehicles or renewables. One of the main challenges, talking about the distribution network, for example, I spoke about the transmission network before, which is the high voltage part of the grid, and the distribution network is the medium voltage part of the grid. The medium voltage network is the one where we are connecting all these things, the distributed generation and the electric vehicles. Then the problem is that the peak that we have of the generation of energy doesn't coincide with the consumption. So when we have a lot of generation, we don't need it. And when we need a lot of energy, for example, at the peak hour, which is at the evening, then there are no renewables, for example, solar. Then there is no sun anymore. So this disparity in the need and the demand and the consumption, it's reflected in terms of voltage fluctuations at the distribution network. There is a voltage fluctuation, for example, when there is a lot of generation but no demand, then the voltage goes up very quickly. And in the other way around, when there is no generation and a lot of demand. And this is very bad in general for the quality of energy. So there are standards that say that there is a limit or boundaries between plus minus 5% of the nominal voltage. You cannot surpass those limits. Otherwise, you are already in a violation of the standard and you can get fined, basically, right? In this case, a distribution network operator, because it produces damages to equipment and lots of troubles in the operation. So now the idea of coordinating the distributed generators is basically, instead of seeing these devices like charging stations for electric vehicles or inverters that interconnect distributed generation into the grid, instead of seeing them as a disadvantage or a challenge, that we can use them as ancillary services. So control them in such a way that instead of being a problem to the network, they are a solution. So this solution is in terms of voltage regulation. So we can assign a set point, for example, for the voltage that we want, and then regulate the injection of power in these devices in such a way that we maintain that the voltage is stable. So that is the idea. That is the challenge of the EVs and distributed generation, and that is the solution that we are not proposing it. It's just how it should be done. The only thing that we are proposing it is how to do it with data and micro PMUs.
So in this paper, you mentioned the objective was to ensure optimal voltage performance across the network nodes. Could you elaborate on how you were actually able to achieve this?
Yes, well, it's a very interesting problem from the point of view of control. We have a difficult problem because we have multiple outputs. This means that you want to maintain the voltage regulated across all nodes in the network, not just one, but all of them. So how to achieve this? It's a difficult problem from the point of view of control. So what we did is devising a voltage performance index that basically represents the voltage, or it's a reference that represents the voltage of all nodes in the network. Then you use this reference to control your inverters or control your ancillary services that I mentioned, the distributed generators or the EV chargers.
Okay, so if it's all right, I'd like to return again briefly just to discussing behavioural systems framework in the context of your application-based work. So it kind of seems to me that the behavioural systems approach seems to be almost like a mindset or a way of viewing problems. So I was wondering, so we mentioned before that you worked on DC-DC converters before your PhD, and then obviously you've done a load of work on it since then. So do you think that having the theoretical background changed the way that you thought about the problem of kind of DC-DC converter control?
Yeah, definitely. I think the main advantage of behavioral system theory is that you can think in general terms, precisely. You are not constrained to think that you need to match your problem into your solution. So with this, I mean that if the system doesn't have this particular representation, which is state space, then I cannot solve it. Either I find a way to put it in there to make it fit, or look for another problem. And that is perplexing from the point of view of applications. So what we do is in the opposite way. We have the problem, and let's work out the best possible solution. And this usually brings either can very well be a state space representation, or can be a transfer function, an impedance, or higher order differential equations. So from the behavioral point of view, since we are not married to a very particular representation, we can just move with more freedom in the deck of solutions or the type of mathematical tools that we can use. In that way, I think I'm very happy, and I was very lucky to work on this framework, because it gives you such level of freedom.
Okay, so I have a few kind of quick fire questions at the end. Is that okay?
Yes.
Okay, great. If you could send a message to yourself 10 years ago, what would you tell the younger Jonathan?
Okay, this is a good question. Well, I would say a lot of things, but I kind of answered this question. I wrote an article that is called Advice from a Young Scientist to Younger Scientists, and I tried to answer this question.
I've linked to this article in the show notes below, and I really strongly recommend going and checking it out. It covers a lot of the points and advice that Jonathan is about to make in a lot more detail, and is also just beautifully written. Definitely worth a read.
Precisely because I thought that there are lots of things that we are not told when we are PhD students. In a sense, being a PhD student is very nice. It's a blessing, because you see only the good part of research and academia. So you enjoy all the nice things about thinking about the problem, how to solve it, the values of science and research. I mean, it's very beautiful, and in a sense, it's a sort of bubble where you live in, a very beautiful one. But as soon as you finish your PhD, then you face the real world, and you see all the cracks in the academia, in the community, all things that can make you feel very depressed. For example, one of the things that I troubles with is finding the best way how to continue my research and how to preserve my values. I mean, how to do things in a very honest way, how to go through a problem, developing a network of colleagues, having always good practices in research. You see that immediately these things are challenged. And I see a lot of people going to the dark side of it very quickly. Other people try to keep their values very fiercely, and they get depressed very quickly. So in a sense, you have to find the way how to do a certain balance, how not to get depressed, and how to keep your values. So I try to answer these questions, for example, how to deal with the teaching, how to deal with the idea of research funding, grant proposals, all sorts of things. I mean, collaborations. I have had very good and very bad experiences with collaborations. So this is a very wide topic, but I would say that I would tell me, my younger self, I would tell to me, this is what will happen. Don't worry. I mean, there is a formula to keep your values and to do the things that you like to do, but you need to be very patient. You need to not to lose confidence, because that is another thing that we can lose very quickly in academia when we get rejected of paper, or when we don't have the results that we expect, or we don't have the time to do the things that we like. So we get depressed and lose confidence very quickly. So what I would tell to myself is, don't worry, just keep going. You will find a way, and don't get depressed when you see negative things in academia. But just try to get the most of it, even with those things.
What's the best piece of advice you'd ever received?
The best advice could be, I think it was from my supervisor, a PhD supervisor. He told me something like, I will never forget. He said, never be afraid of learning new things. And I think that has been a constant in my career. For example, I'm working now on cybersecurity. I mean, this looks like madness. I mean, going from power converters and control, and then cybersecurity out of the blue. I mean, it's because I have always had this idea of learning new things. In a sense, I keep the core knowledge that I have, but I'm never afraid to learn about a new application. So this has given me the advantage to work with all sorts of things, simply because I'm not afraid to show my deficiencies, let's say, or my weaknesses to my colleagues. I'm quite open, and I think I learned that from my supervisor. He said that explicitly.
Are there any fields of control you haven't worked in yet but would like to?
Well, I think I would like to work a little bit more on nonlinear systems. I did a bit of it with this lifted coordinates idea. I would like to explore more about nonlinear systems. And as I said, I'm also interested in cybersecurity from the point of view of control theory. So how to detect cyber attacks from the data, and how to deploy the adequate countermeasures in the controller to act upon such attack. Either a stop in the data stream, for example, from sensors, or even if you have completely fake data injected into your communication channel. Now, how you detect it, and what is the best thing that you can do for that, for example, to preserve stability.
What's your favorite part of your job?
Well, I like, in general, my job. I mean, I like teaching, for example, but definitely is research. I mean, I wouldn't do anything else. That is the reason why I haven't gone to industry, because I like the freedom that I have to just think about new problems and solve them and spend time solving those problems. And also, I like very much writing. So writing ideas, writing papers is something that I deeply enjoy.
Who is your role model within the field of kind of control or mathematics?
Uh, my role model, well, it's difficult to say. I admire so many people. I mean, of course, I admire my supervisor. I admire perhaps Arjan van der Skaft. Is from the Netherlands. He wrote a very famous book on nonlinear systems. I admire his work on Port Hamiltonian systems. I think it's very, very good. Is very talented in mathematics, and he has a good grasp of the physical interpretation of things. Port Hamiltonian systems are basically a signature of him in that regard. That is from control and mathematics. From the engineering side, I admire people like Johann Kohler, for example. He's from ETH Zurich. Is a very good engineer in terms of magnetics. He has a whole school of very brilliant people in the area of solid-state transformers. And I admire how he has managed to develop this strong group and also having a lot of applications in real-life applications for industry.
Great. So final question is, what's been your favourite paper or project to have worked on?
I think in terms of the paper, I liked very much the paper that we wrote about dissipative switch linear differential systems. I think it's a very good paper because we spent so much time on it. I have never had the same level of revisions that we go through. I mean, the same level of detail and rigor for other papers. So that one is very good. And the project, I like very much the project about with the University of California at Berkeley on micro PMUs. That was a very good one because, as you can see, it brings this part of the practical application, in this case distribution networks, that matches very much with my background in control and what I like to do, in this case data-driven control. So I deeply enjoyed this.
Great. Thank you very much for the interview.
Yeah, thank you for having me.
So this episode has been a deep dive into a few of the possible applications of behavioural systems theory and data-driven control. So we have learnt that switched linear differential systems are composed of a set of behaviours and the associated gluing conditions that specify what happens when you switch between each of them. We've also learnt that DC-DC converters are designed to increase or decrease DC voltage, and controlling them to maintain a constant output voltage is way more difficult than you might think, especially in cases when they're connected to a constant power load. However, it is possible to control them, for example, by shaping the dynamics of the system to induce passivity, or by lifting the nonlinear coordinates into a different frame so that they become linear. And we have also learned that a good way of controlling DC microgrid configurations is to use data-driven control, in which you get information from the data itself by generating a coefficient matrix and then using this to parameterize the system and derive controllers. I really hope you've enjoyed this episode. I really loved sitting down and talking with Jonathan. You might have noticed I kind of stopped editing in asides towards the end of the episode because firstly the episode was getting really long, and also Jonathan was just explaining everything so well. There wasn't really anything I could think of to add to clarify anything. A few times towards the end of the episode, Jonathan started talking about cybersecurity, which, if you remember, was something Paolo mentioned very briefly at the end of last month's episode. And I really wanted to ask about it in more detail, but by that point in the interview, we were already overrunning by like 20 minutes. So I'm thinking maybe in future, I'm going to do a follow-up episode where we can go back, interview Jonathan, maybe talk to Paolo, find out more about this. There's also another academic at Southampton called Konstantinos Gatsis that I would love to interview. I've read so many of his papers and they're honestly so good. Next month's episode will hopefully be released on the 1st of June. As of this recording, I have no idea who that was going to be with, but I have a few guests in mind. All of them do research into different controllers or applications that we haven't covered yet on the podcast, so I'm sure it will be very interesting whoever it ends up being. Until then, though, as always, I hope you have a fantastic month.